Let's talk about displacement current. Now, I want you to imagine a capacitor being charged. It's a parallel plate capacitor like this. And there is some current going in, and it gets charged. This one gets plus, this one gets minus. So normally, we would apply Ampere's law over here. Right? Normally we would say that at a distance r, let's say, can I draw it actually a bit larger? At a distance r over here, it's actually closer, but for the purpose of this, what I'm about to do, let me draw it larger. So I can say that integral b dot dl is mu 0 I. Do you agree with this? Which tells us that b times 2 pi r equals mu 0 I. And in this case, b will be pointing in this direction. Right? What I haven't told you is that when we are talking about this law, we are actually secretly talking about an area as well. We are actually talking about an area generated by this loop, and we are counting all the currents going perpendicular to this area. Okay? So what you can do is you can stretch this area while preserving the loop. You can, for example, stretch it like this. Do you see what I did there? You can talk about that area. It's like butterfly catcher again. Okay? But this time, what I did is I stretched the area in between the capacitors, right? So as a result, there is no enclosed current that we can define of, right? So far, did you follow all this? So if you look at the green area, there is a current penetrating it, and there's no problem with this law. But if you look at this red area, there is no current penetrating it. Okay? So we have a problem. That brings us to Maxwell's corrected Ampere's law. This is the thing that I talked to you about right in the first lecture, the thing that Maxwell brought to electromagnetism, some sort of symmetry. All right? It's time to realize what that symmetry is. Maxwell, let me first write to you Maxwell's corrected version. Maxwell tells us that B dot dl is still mu 0 times enclosed current, but it includes something called displacement current. Okay, ID in this case is defined as epsilon 0 times d phi e over dt, and this is named as displacement current. First of all, let me show you that this displacement current in our example is exactly equal to the enclosed current. So what I'm going to show you is the following. So if you have this part, then displacement current is 0. All the current there is this I. Okay. If you look at this area, there is no normal current, charge current. There is only displacement current, and hence these two must be equal to each other. Do you see the point? Because it's I plus ID. In the green case, this is I, this is just simply I, and this one is 0. In the red case, this one is 0, and this one has to be I, so that it's the same thing. Okay? Let me show you that it is the same thing. Let's draw this again. So we were talking about this system, right? Maybe I should. So there is an electric field between these plates, and that electric field depends on the charges, right? This is plus Q, this is minus Q. What do we know? We know that electric field is sigma over epsilon 0, which is Q over A times epsilon 0. Then dE over dt is 1 over A epsilon 0 times dQ over dt. What is dQ over dt? I. It is I. Very good. So then I can write I equals to epsilon 0 A times dE over dt. And I can write this down as epsilon 0 times E times A over dt, which is epsilon 0 times d phi E over dt. Do you see? So our displacement current is equal to the I mentioned in the problem. Okay? So just for the sake of stealing a bit of your time, let me just write it down one more time. This is Maxwell's corrected Ampere's law, and this part is current due to charge flow, and this part is displacement current due to change in electric flux. Okay, so now I can just, this is Maxwell's correction. What it is telling you mainly is that just like changing magnetic flux creates electric field, changing electric flux creates magnetic field. This one. Thank you. All right. So let me give you an example of this, or let's first write this one. Changing electric field, electric flux generates magnetic field. Okay. Similarly, changing magnetic flux generates electric field. This is the nice symmetry that Maxwell pointed out.
Wouldn't it be better to write B fields instead of M field?
Thank you very much. It's more symmetric. Exactly. So let me give you an example. I have a region that has a radius of r, and there is an electric field pointing in to this region. Okay, and this electric field is changing. Electric field is, let me just write it down like this. dE over dt is alpha and it's greater than 0. So the question is, what is the magnetic field at a distance r inside or at a distance r outside this loop? That is the question. So let's start with the inside, right? For inside, you can write down Ampere's law, but Maxwell corrected version of it. B dot dl inside must be equal to mu 0 times I plus id enclosed. So what is I enclosed in this case?
I displacement. There is no charge, right?
There is no charge flow. So this one is 0, right? And ID is, so let's find ID. ID is
times A.
what?
JD times A. I mean, we will have a current density. Current density times A is the I current for that area.
Why not go with epsilon 0 d phi e over dt?
You could do that as well, but it is the same thing.
But there's no j. There's no I, there's no j.
Actually, I could.
Okay, so
J would be in that case, like if we think of idealized displacement for area, the delta phi e over dt, and you divide it by A, the total area, then the J is just epsilon 0 dE over dt.
yes, but
You get the same thing.
yes, but j is reserved for charge flow. There's no charge flow here. It's just electric field changing. Okay?
Because there is no charge flow, you said that I is 0, right?
Yes. So epsilon 0 times area. What is the area?
Area is 2 pi r squared.
Pi small r squared times dE over dt. And by the way, notice that there is no negative sign in front of this. So in the Faraday's law, there was a negative sign in front of magnetic flux generating the electric field. This time there is no change. There is no negative sign, so you don't need to think about Lenz's law in this particular case. So B times 2 pi r, because that's the length, is equal to mu 0 times E0 times, mu 0 is from here, okay? Pi r squared times alpha, right? So B is equal to mu 0 epsilon 0 times alpha times r over 2. Is that right? This is my magnetic field for r smaller than r. Do you have any questions at this point? Any questions? No? How about when I'm outside of this loop, where the electric field is applied? You know this black dashed curve that delineates the place after which there is no electric field. So outside, the electric field is 0. So we are only applying electric field inside this circle. Hence, for outside, integral b dot dl is b times 2 pi r, but that is equal to mu 0 times epsilon 0 times pi big R squared times alpha, not pi small r squared. So the electric flux is applied only to this area, not the whole area. Okay? So there is a slight difference here in magnetic field outside. Outside this region, the magnetic flux will be mu 0 epsilon 0 alpha small r squared over 2r. Okay?
What is wrong with
Okay, yes.
Also, can you show the direction of the...
One moment, just one moment. Yes.
Can I show you something?
Wait, one moment.
Can you also show the direction of the magnetic field?
Very good point. Can I show the direction of the magnetic field? Yes. It is pointing, so it's not against the change in electric flux. It's in the same direction. So change in the electric flux is inwards because it's pointing in and it's increasing. So magnetic flux will be generated in this direction. Magnetic field will be in this direction. Also, magnetic field outside will be in the same direction. Very good point. Yes, tell me, Ali.
It is better if I should try doing the book. Can I?
Yes?
The concept of displacement current density is used by Clerk Maxwell.
Ah, okay. Thank you very much. Okay. Good. Any other questions? Comments? Ideas? So we have 15 more minutes. And let's start with a new chapter. Okay? And quickly finish it tomorrow. Then we can solve questions. I hope you have been following everything. Chapter 30, Inductance. So this chapter starts with the idea of mutual inductance. Okay? So, what is mutual inductance? I want you to imagine two loops, one going like this, two solenoids wrapped around each other. So this one has a current I1 and number of turns is N1. This one has a current, we don't care about the current in the other one yet. The other one has N2 turns. Okay. So here is how you define mutual inductance. Here is how you define it. Mutual inductance 2,1 is N2 times phi because of the second one divided by I1. Now, what does it mean? Yes?
I mean, phi can be found by B times A, and that B is created by the solenoid with the current going inside it.
Mm-hmm.
And what are you really asking?
No, just that. So this is the definition, and it turns out that whichever way you do it, you are going to get M12 equal to M21. Let me give you one more step in this calculation, and it will be clear why we are defining it. So E2 will be negative N2 times d phi B2 over dt. Right? EMF generated in the second loop will be negative N2 times change in the flux in the second one, right? So if we take the definition of M21, we will see that it connects, if we plug it in here, it connects the change in the current of the first one to the EMF created in the second one. Do you see it? So the EMF created in the second loop, because of the change in the first loop, can be described by this M21. M21 is just the coefficient in front of this. Okay? We will calculate the mutual inductance in a moment, but first of all, let me describe the units. As I mentioned earlier, it turns out that M is M21 equals to M12. So the mutual inductance between 1 and 2 is equal to the mutual inductance between 2 and 1. What is the unit?
Weber per amperes.
Very good. And we have a name for this one. Do we call it Henry or Henri or something like that? Henry, right? Weber per 1 ampere, which is ohm times seconds. Okay, let's give an example, and this example will be very useful to understanding everything here. Can I think for a little bit? So I'm actually going to use this very loop, this very system. So let me copy it, paste it in here. But I'm going to change the values. So, oops, sorry. So I'm going to use this first one as N1, the second one as N2, and the first one will have an area. Let's say the area over here is A1. Okay? So I want to find phi B2. What is phi B2? Because of the first one. So what is the flux generated in the second one because of the first one?
B2 times A1. B2 is equal to...
B, yes. You mean B1 times A1, right? That's the thing with these indices. The current is in the first one. Okay, so let me call this one I1. Do you remember the magnetic field generated by the...
N0 something like that.
Do you remember the magnetic field generated by the solenoid? Anyone?
N0
Yes. So it was So let me just start with magnetic field. The magnetic field generated by the first one will be mu 0 times N1 over L1. Let me call this one L1 times the area A1. Oh, sorry. Times the current I1. Okay? So the magnetic flux, let me ask you this one. Which one is easier, to find the magnetic flux generated by the first one going through the second one, or the other way around? Which one is easier? Do you understand the question? Which one is easier? I generate magnetic flux in the blue one, and how much of it goes through the green one, or I generate magnetic flux in green one, how much of it goes through blue one? First one is easier because we are sure that all magnetic flux is going to go through the second one because it's inside the second one. Okay, so magnetic flux in the second one is simply B1 times A1. Okay. Now remember, the mutual inductance was defined as N2 phi B2 over I1. So let's put everything together. I have M equals to N2 over I1 times B1, which is mu 0 N1 over L1 times I1 times A1. Is there any cancellation here? Just this one, right? So what I get is, it depends only on geometry, N1, N2 times A1 over L1. That's our mutual inductance, yes. And this will be the same whether we did it with respect to the second one, or second with respect to the first one. It's the same thing. But this one is easier to do. Okay? So far so good? Now let's talk about self-inductance. So far so good. Let's talk about self-inductance. In the case of self-inductance, both wires are the same wire. So I only have one wire, and I'm wondering how the change in this current affects the EMF in that loop. So I have the area A, I have the length L, and I have number of turns N. And L, self-inductance L is self-inductance. L, you simply drop all the indices, okay, N phi over I. This is what self-inductance is. And from previous solution, we can assume that this coil is both of these coils in here. It's like these two coils are right on top of each other. Okay? So that's why you just drop the indices, and L turns out to be mu 0 N squared times A over L. That's what your self-inductance is for a solenoid. So this is self-inductance of a solenoid. Let me write that down. Of a solenoid. Okay? And also, what we have learned here is still true. What we have learned is that E2 was negative M21 di1 over dt. Now drop all the indices and make this ml. Then you can just simply write the EMF change in a solenoid, in an inductor that is interacting with itself, is this one. Okay? That completes our tool set. You remember we talked about analogies. This is what we call an inductor. This is the inductor. A solenoid by itself is an inductor because its EMF is affected by the change in its current, right? So what does it tell you? Let me remind you what we had before. We had capacitor that looks like this, and EMF of the capacitor was Q over C. It was directly proportional with the charge on it. We had resistor, and for the resistor, ohmic resistors at least, it was I times R, which tells you that it's R times dq over dt. Do you see? EMF depends on the first order derivative of the charge, right? Finally, now we have an inductor. Okay. Inductor, and for the inductor we have just written this law, di over dt, and that corresponds to minus L times d squared q over dt squared. So if you remember earlier, we made an analogy with mechanical systems in RC circuits, and we said that think about this one moving inside honey because it didn't have inertia. Well, now we have the inertia term. Okay? What inertia tells you? Inertia tells you that if something is moving, it wants to keep moving. Okay? Or if something is not moving, it wants to keep not moving. That's what inertia is, right? Similarly, inductor is the inertia analog of electric systems. In this case, if there is a current and if you have an inductor, the larger the inductor, the more massive it is. You can think of it like a mass, and the more it will resist against current changes. Okay? Current, is there a current flowing? Is there an inductor? It will want to keep flowing. So you don't have honey anymore. You have massive object that wants to move if it is moving. If there is no current, it will be harder to generate current in this system because of this inertia. Okay? This is a good place to stop.